Hello, my name is Dmitry Khomchenko. Welcome to this video. Today we will talk about link loss compensation and amplifier placement in XHaul optical networks in general and in front-haul optical networks in particular. First of all, there will be a few words about why do we need amplifiers and sometimes DCMs in front-haul networks. What should we keep in mind when we do loss compensation? For instance, where we can add amplifiers to design a feasible network. Available equipment and its parameters are also important, and of course engineering rules used during the design process. Eventually, we will go from the manual design through the automated one to application examples. Front-haul networks evolve constantly and become more sophisticated, and nowadays a separation of front-haul and back-haul networks disappears. Due to constant traffic growth, DWDM technology along with high bit rates and sophisticated modulation formats become important in front-haul networks. As a result, high link losses, which include loss of optical fibers and DWDM equipment, for instance multiplexers, and stringent requirements to quality of services require amplification of optical signal. Along with the power budget of the light path, the location of amplifiers should also be accounted. The next thing that should be kept in mind is the quality of service at the receiver point. In other words, optical signal should meet the receiver operating ranges, for example, minimal required OSNR and optical power. On the other hand, an equipment available for design has also its own limitations. For example, an amplifier is characterized by wavelength-dependent gain, noise figure dependent on gain, and operating power range. It is also worth to keep in mind future traffic growth when amplifiers are added, in order to avoid network redesign in the nearest future. And on top of topology constraints and equipment limitations, there are engineering rules, which differ for different engineering teams or different equipment libraries. So, when an engineer starts solving the link loss compensation problem, she or he should check a lot of parameters along with the received optical power. One more thing is the complexity of network topologies. Quite often engineers deal with mesh networks rather than with simple point-to-point transmission lines, and the mesh network contains rings or optical loops. Typically, the network configuration is built on a link-by-link basis and local decisions are made when amplifiers are added. Eventually, the solution is ready, but the question is, if it is possible to build a configuration with better performance metrics or with lower cost of added equipment, so design of another solution starts. And if equipment limitations are difficult to violate, the engineering rules are bent quite often. We offer the algorithm which applies a unified approach to all links in the network and builds a solution for the whole system, taking into account equipment limitations and topology and engineering constraints. It is also able to generate solutions either for a newly designed network or for a network being upgraded, for example with respect to new services added to an existing network. Our approach uses two separate algorithms for link loss and dispersion compensation problems in order to accelerate the design process. The dispersion compensation is a mixed integer linear problem and it is solved by third-party software. Sometimes the second run of LLC algorithm is required to account for an extra loss introduced by standalone DCM along with the received optical power and OSNR penalties caused by residual dispersion. So, along with the LLC algorithm itself, we developed the script that automates the whole workflow and synthesizes equipment configurations for LLC and DC problems, visualizes solutions with key metrics, and configures equipment within network design environment. Now, let's have a look at 4 scenarios of LLC and DC for a slightly extended front-haul network recently studied. At first, there will be loss compensation without constraints to amplifier placement and accumulated dispersion. That is, the signal metrics are just to meet receiver operating limits. Then, there will be use cases when amplifiers are not allowed in the inner ring, and stringent constraints are imposed on accumulated dispersion. For all use cases, power and OSNR margins required at the site are 3 dB. In other words, the optical power and OSNR at any receiver in the network should be 3 dB higher than the threshold values. In the first use case, the algorithm generates solutions with 3 amplifiers and no DCMs. Signal power, OSNR, and dispersion maps are shown for the longest light path in the network. On the left side, metrics are shown for the initial equipment configuration, that is, without amplifiers, and on the right side, the same maps are shown for the selected solution. There are 2 amplifiers added to nodes N3 and N5 in west-east direction, and 1 amplifier is added to the node N3 in the reverse direction. In the second use case, the algorithm generates solutions with 5 amplifiers. The lower OSNR is the result of constraints imposed on amplifier locations, as it is seen on the right side. The amplifier is added to the west-east direction right before receiver, in other words, after total loss of all fibers in the light path. In the third use case, 4 DCMs are required along with 3 amplifiers due to stringent constraints imposed on accumulated dispersion. As it is seen from the dispersion maps, per-channel values of accumulated dispersion lie within the receiver limits, but are above tolerance specified as engineering constraints, even for the shortest light path in the system. So, the synthesis script runs as LLC, so DC algorithm, in order to build the solutions. The lower margins in the solutions are caused by another amplifier locations and extra losses of standalone DCMs. However, the solutions still contain 3 amplifiers as in the first scenario. And for the last scenario with stringent constraints imposed on amplifier placement, so on residual dispersion, the solution have 7 amplifiers and 4 DCMs. Just a small conclusion here instead of signal metrics charts, which are pretty much the same. Typically, more expensive configuration of equipment are required for a network with more complicated topology or more stringent design constraints. An example is an upgrade of services when 10 gig signals are replaced by 25 gig signals with another modulation formats. In this case, there will be another thresholds and more stringent constraints, which could also lead to more expensive solutions in terms of added equipment. Now let us summarize. We demonstrated the algorithmic approach, which offers an efficient way of link loss and dispersion compensation. Our synthesis script automates the design refinement. The approach is flexible enough to accommodate optical network topologies of different types and provide equipment configuration for networks designed from scratch or networks being upgraded, for example with respect to traffic growth. The algorithm accounts for available equipment, optical channel parameters, design constraints, and generate cost-optimized solutions with optimal amplifier placement. Thank you for your attention. If you have any questions, please write me an email.